You'd understand if you were the leader of his algorithm.
Okay, folks, we can get rolling. Let me just make sure I'm recording. Yeah. Okay, any questions from anyone before I get into content for today? Lab 1 going okay for folks? Anyone get any swooping or chirping just yet? Yeah? Awesome. Okay. So let me just remind you then what we've been doing here in lecture. I'll just remind you that what you will be doing in Lab 1 is integrating and then augmenting 2 pieces of demo code. One of those pieces of demo code is the audio beep beep demo that we've been spending a considerable amount of time in lecture generating an understanding for. And in fact, we've pretty much covered every detail of that particular demo with one dangling bit, which is fixed point arithmetic. And I'm going to delay that conversation to Wednesday, because I think the most useful thing to talk about for your lab checkoff this week is the other piece of demo code with which you will be integrating the beep beep code, which is the keypad. And many of you have already gotten the keypad set up and tested, and that's awesome. If you poke through that keypad code, it can look a little bit cryptic, and so I thought we'd take some time today to explain what exactly is going on there. And I'll just mention too, this lecture, as with so many of them, if you read the keypad cage, much of the content from this lecture is there. So if you want to go look at that, you could do so. So let me start actually by pulling up the keypad demo. Let's see. So the one that we've been discussing is this audio beep synth single core. I want to talk today about the keypad. So let me open that up. And if we take a look at this, what I want to spend some time discussing in particular is, you may have noticed that scanning the keypad involves these sort of cryptic looking scan codes and key codes and so forth. So I thought we'd just talk a little bit about what's going on there. So unless there's any questions about anything else, I can get into this. Okay, so the keypad is the internal schematic of the keypad is it's a switch matrix. And so those of you that have already hooked the keypad up, you will know that there's 1, 2, 3, 4, 5, 6, 7 connections coming out of the keypad. 4 of those connections are connected to the rows of the switch matrix, and 3 of those connections are connected to the columns of the switch matrix. When I, the user, push a particular button on the keypad, what I am actually doing is shorting the pin connected to that particular row to the pin connected to that particular column. So for instance, if I were to push button 2 there, I would effectively short GPIO 9, the row 1 pin, to GPIO 14, the row 2 column, or the button 2 column. So the mechanism by which we actually scan the keypad is we start at the first row. So when we're not scanning the keypad, okay, let me back up for a moment. The way that we're going to scan the keypad is we're going to drive the pins connected to the rows as outputs. We're going to control the voltage on those pins from the microcontroller, from our code ourselves. And we're going to treat the pins connected to the columns as inputs. So the mechanism by which we will see if a button is pushed is we'll go 1 row at a time, and we'll set the voltage on the pin connected to that particular row high. And then after having done that, we'll check the voltage on each of the column pins and see if any of those have gone high. In the event that the voltage on a particular column has gone high, then we know that it must be the case that that row, which we've just set to high voltage, must be shorted to that particular column, and therefore the associated button must be pushed. So, for example, when we're not scanning, our input scan code, to use the vocabulary that's used in the demo code, is going to be all zeros. That is to say, the voltage on all of our input GPIOs there is low. And because we're not pressing anything, and furthermore, we're not driving anything, the voltage on all of these will be low. These, by the way, the voltage on the output pins are low because we have told them to go low. We've driven them out as low outputs. the voltage on our inputs are low because of these pull-down resistors. These pull-down resistors, I'll just remind you, are internal to the microcontroller. Every GPIO has a internal pull-up and pull-down resistor that can be turned on from using the C SDK. We have turned on the internal pull-down resistors here, so you do not need to breadboard these. I'll just remind you, the reason that we need these pull-down resistors is that these column GPIOs are inputs. Inputs means they're high impedance. And so if we did not have one of these pull-down resistors here, and furthermore, we were not pushing any of the buttons in this row, what would be the voltage on our input? It's undefined. It's sort of like a little antenna. You know, the voltage is just whatever it happens to be. It floats. And so what that means, if we did not have a pull-down resistor, is that we may sometimes think that this GPIO is high because it floats high. Other times it may float low. By having the pull-down resistor here, whenever we are not pushing any button, there's no current flowing across this resistor. The voltage on this side of the resistor is low, so the voltage on this side of the resistor must be low, and so that GPIO is pulled low. If we were to say we were pushing button 2 and driving GPIO 9 high, right, then when we push this, the voltage on this side of the resistor would go high, and we would measure a high voltage. So by having that pull-down resistor there, we guarantee that that pin is only going to be in one of two states. It's either going to be high when we push the button and we're scanning that particular row, or it's going to be low when we are not scanning that row and it's not connected to any high voltage. Does that make sense? Okay. So let's suppose that key 8 is pressed. And I want to walk through an example scanning of the keypad. So key 8 is pressed. We start scanning the keypad with the first row. So we're going to hold GPIOs 10, 11, and 12, rows 1, 2, and 3. We're going to hold those low. And we set GPIO 9 high. And we check the value of each of the columns. If button 8 is pushed, that means that we've shorted GPIO 11, this row with this column. We aren't going to measure any change here in any of the columns, right? Because we haven't shorted the high voltage to any of the low voltage pins. Okay, so in other words, our scan code would be 1, just GPIO 9 is high. Our output code, which includes both our rows and our columns, would be 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, just our one input. Okay, so no buttons in the first row are pushed. We would then do the same exercise for the second row. Our input scan code would now be 0, 0, 1, 0, right? Just row 2 is high, for row 1 if we're 0 indexing. And because we haven't pushed any of the buttons in row 2, we're not going to measure any of the columns go high, right? And so our output remains all zeros there at the bottom. When we finally get to row 3, right, we'll once again zero all the rows except the one that we're scanning. Now, however, when we measure each of our columns, we will notice that GPIO 14 has gone high because we've shorted GPIO 11 to GPIO 14 through button 8 there. And so the output that we'll get is 0, 1, 0, the middle column is high, and then our scan code, 0, 1, 0, 0, which if you translate that to hex, what you get is 0x24. So we're going to, if you just make, this is the source of some of those sort of cryptic looking scan codes and key codes and so forth. All that we're doing is translating our GPIO state in a number of different conditions where each of the separate buttons is pushed to hex codes, and what we get is these somewhat cryptic looking key codes coming out. This perhaps raises some questions. What if I push both buttons 1 and 2? If I push both buttons 1 and 2 and I scan row 1, I'll measure both GPIOs 13 and 14 going high. In the particular keypad scanner that exists in your demo code, it interprets 2 buttons pushed at the same time as invalid. You don't have to change that. You can if you want to. You can make a more sophisticated keypad scanner. But it will interpret 2 buttons being pushed as invalid. you can imagine that the key code that would come out of there would be 0, 0, 0, 1 on our inputs, and on the outputs we would get 1, 1, 0, right? Which is just, it's not going to exist in our key codes, and so we ignore it. Another thing you might do, though, again, this is not, you could update this if you cared to, but what if we pushed buttons 1 and 5 at the same time? Our scanner, as I've described it, would start at row 1, it would set GPIO 9 high, and it would go, oh, one of my outputs became high as well. GPIO 13 became high, and it would get a valid key press out, and it would report, even though we've pushed both 1 and 5, it would report only button 1 as having been pushed. For our purposes, that's fine. That's not something you have to correct. I'm just pointing that out because that's a common question from astute students, right, is to point out these sorts of corner cases. You could absolutely rewrite a keypad scanner that accounts for those sorts of cases. Ours at the moment doesn't. Why do we need the 330 ohm resistors? It is. So let's suppose, remember, GPIOs 9, 10, 11, and 12, those connected to our rows are outputs. Outputs means low impedance. It's easy for current to flow in and out of these things. So let's suppose we did not have the 330 ohm resistors, and me, the dumb user, pushed 1 and 4 at the same time. Well, when I scan row 1 now, GPIO 9 is going to end up being shorted to both GPIO 13 and GPIO 10, right? Because I've closed both those switches. If I did not have the 330 ohm resistors there, I'd send a bunch of current right into GPIO 10 and blow it. So the 330 ohm resistors there are there to protect you from yourself. You need to have them there. Any other questions about this? Okay, so if you apply this sort of, this is the logic that we're using here. We are enforcing that the only valid key presses are one key at a time. We're scanning the keypad by going one row at a time, set it high, see if any of these went high. If one of these went high when we set one of the rows high, that's a valid key press. We figure out what's the row column that's connected. If 2 or more of them went high, that's invalid. The user's pressing more than one key. So we did an example. We walked through every step of the example with pushing pin 8 there. This is every possible press, right? And so if you look at the scan codes here and the control codes, those of you with very good memories might recognize some of these hex values from the somewhat cryptic arrays in the keypad code that we'll look at in just a moment, right? But this is showing you for each control code, that is to say the value that we send into the rows, the valid scan codes that we might get back out. If we send in a 1, we just set the first row high, and the scan code that we get back out is also 1. That means nobody's pressed any buttons, right? These different codes are associated with one of the 3 column GPIOs going high. Does that make some sense? So then when we encode this, right, here are all of our key codes arranged such that their index in this array maps directly to the button, right? So the key code associated with pushing the button 0 is 0x28, with pushing button 1 is 0x11, with button 2 is 0x21. And if we were to look back at that table, we would note that if we push a button, if we push 0, the scan code that we get is 0x28. If we push button 1, the scan code that we get is 0x11, and so forth. And so the numbers in that array are coming from this logic. And furthermore, if you look at our scan codes, right, these are the values to which we're going to set each of the rows as we scan the keypad. You'll see that all we're doing here is shifting a bit, a one-hot bit through each of our rows. So to scan the first row, we just send 0001. To scan the second row, we send 0010, and so on, right? So these are our 4 scan codes for each of our 4 rows. For each of those scan codes, this is the list of all of the valid key codes that might come out. Now, like I said, this particular key scanner only allows for one button push at a time. If you wanted to allow for more than one push at a time, one way that you could do that is by adding to this list of valid key codes to include those that might include multiple buttons. Or you could scan the whole keypad once, right? Don't stop once you find a valid key code in row 1. Keep going and see if you find any other valid key codes. Would be another approach. That would work for keys in different rows, not keys in the same row, though. Okay, so then how does a scan actually work? This is, oops, what did I do? Escape. This is the thread which implements the keypad scan. Notice a few things about it. Like we talked about last time, each of our threads begins with a PT begin and it ends down here with a PT end. Before our internal while one loop, we've declared a couple of static local variables, an integer called I and an unsigned int called keypad. Remember, static because these are local to the thread, and so we want for them to be stored globally but scoped locally, so we make them static. And then all that our keypad scanner does is at the beginning of the thread, it puts the GPIO high, and at the end of the thread, it puts the GPIO low, somewhere down here. Oh, I'm sorry, it toggles it every time we schedule the thread. This is to give you a visual indication that your threader is running. And by the way, it's just a good practice to give your code a heartbeat, a visual heartbeat. Schedule a thread that just blinks the LED, or have one of your threads blink the LED so that when the thing starts running, you have some visual indication that your threader is running. That can save you a lot of headache, just that very simple sort of visual feedback. So the first thing we do is just toggle an LED, and then we go through, and for each of the rows in our keypad, key rows here is just 4, right, or 3 for 0, 1, 2, and 3 rows. We go through and we set the GPIO outputs to be each of our valid key scan codes. So we start with just setting GPIO 9 high, then 10, then 11, then 12. So we set the outputs. We sleep for a microsecond. Why would we sleep for a microsecond? It turns out this does not work if you don't have a small delay between setting the outputs and reading the column inputs. Why would this not, this is subtle, why would this not work without a small delay there? Very close. The proposal was inductance in the lines. The answer, as it turns out, is the capacitance of the breadboard. So the breadboard has internal capacitance. If we look back at our keypad diagram here, right, the breadboard has capacitance. You could imagine that the breadboard itself acts like a little capacitor here connected in parallel to ground. It takes non-zero time for that capacitor to discharge through our pull-down resistors. We have to wait for that non-zero amount of time for that to actually discharge before we'll get a valid key code out. This is another example of when you're building things in physical reality, physics is included in your debugging environment, right? We did not put a capacitor there, but physics imposes a capacitor there, right? And so that's why the little delay exists. But okay. So we set our rows, we wait for a little bit to allow for discharging through our pull-down resistors, and then we read the state of our GPIOs, and we store what we've read in a value called keypad. And I'll just mention that there's some shifting occurring here and some masking. When we call GPIO get all, that gives us the state of all 31 or 32 of our GPIOs. All that I'm doing here is shifting out the lower ones that I don't care about and then masking so that I only retain the bits associated with the GPIOs connected to the keypad. Right, so I shift out everything I don't care about by shifting out by base keypad pin, GPIO 9, and then I mask with 0x7f, so I only retain the bits I care about. And then I do a quick check here. If keypad and button break, what is button? Button is just a little shorthand here. 0x70. So what I'm effectively checking there, 0x70, what is that? 111 in the most significant bits, followed by 4 zeros. So by checking keypad and 0, what I'm asking is, are any of the buttons pushed? I'm then going to subsequently figure out which button is pushed, but just to do this as quickly as I can, I'm first asking, are any of the buttons pushed? In the event that one of the buttons is pushed, we break out of this for loop, and then we go through each array, each key, each element in that array of valid key codes, and we ask, is the value that we read from the keypad equivalent to that particular index in our key code array? In the event that there's a match, then we know that that's the button that was pushed. Okay, so we go through, let's say we're pushing button 2, right, first row. So we go through, button 2 is pushed in the first row. We hit this first for loop. We set the GPIO associated with the first row high. Wait a little bit. We read back the key code. And we notice that the key code that we've gotten back has bits that are 1 in the section of bits associated with the column. And we say, okay, at least one button's pushed. Let's see if it's a valid key code. So then we go through and we check every element of that valid key code array against the key code that we read. As soon as there's a match, we stop. If we don't find a match, then that must have been an invalid key code. Maybe the user was pushing 2 buttons, right? But in the event that we get a match here, in this case, we would get a match on index 2 of that array. We would say, there's a match. We set the, there's a match, so we break. Our iterating variable I has now assumed the value of the key that was pressed, right? If we broke on index 2, I now has 2. If we got through this for loop and never broke, that means we never found a valid key code, and we set I equal to -1. So those of you that have run the keypad demo code, you will know that all that keypad demo code is doing is printing out the value of the key that's being pressed. It's actually reporting the value of that key via 2 media. It's putting it to the VGA screen, and it's also printing out via the serial monitor. You don't need to hook up the VGA screen, right? You could if you want to. We're certainly going to in Lab 2. But just for purposes of checking your keypad connections, you could just hook up the serial monitor. And you will notice, many of you already have, that when you hook it up and you just start running it without pushing buttons, just streaming out -1s. Here's where the -1 is being set. This is just no valid key code. As soon as you push a key, it will print out the value of the key that's been pressed. The way that it knows the value of the key is that is as far as it got in this for loop through each key looking for valid key codes. I got to index 5 and I found a match. Button 5 was pressed. So then all this does subsequently is, like I said, it reports the value of the key to the VGA display. It also prints out the value of the key. And then it yields, this thread yields for 30 milliseconds. Why 30 milliseconds? Because I sat in the lab with a keypad and went boop, boop, as fast as I can. And I can't push 2 buttons faster than about 30 milliseconds. So that seems like a pretty good scan rate. Any questions about this? So you will have to augment this with a debouncer, and that's the next thing that I'm going to talk about. Each of the buttons on this keypad, again, remember, we're in the physical world here. These are all physical buttons. A physical button is pretty well modeled as a spring mass damper system, right? When you close a button there, what you're doing is actually closing a physical switch. Because it's a physical switch, it's going to bounce. So when you push 1 down, it doesn't just go from an open circuit to a closed circuit. It goes open, closed, open, closed, open, closed, open, closed, and it bounces shut. Essentially all physical buttons do. That is of relevance to us because that means it leads to the possibility of, well, it could lead to 2 flavors of bug. One flavor of bug that it could lead to is we push button 1 once, and our code thinks that we've pushed the button 2 times, 3 times, 4 times, however many times it bounces, right? Depending how quickly we're scanning the keypad. Another bug that it could lead to is we push the button and we get unlucky with the timing of our keypad scan for one of our scans, and it's bounced open and we read it as open. And so what we need to implement is a debouncer, In our case, it will be a software solution to this problem, though as some of you have pointed out, you could certainly solve this problem in hardware as well. And if you would prefer to do that, you're very welcome to do that. So what we are going to do is debounce this thing so that we only report a button as having been pushed when we measure it in a stable state. The bouncing has stopped. So what does that look like? It takes the form of a rather simple state machine. This state machine that I'm about to describe is going to live here. Here's where the debouncing goes. Okay? So you schedule your keypad thread. It scans the keypad at the top. And once you get through the scan, that variable I contains the value of the key that's being pressed, or -1 in the event that no valid key press is occurring. Right? So that's the scan. Here, after having scanned the keypad, is where we're now going to debounce that to make certain this was a valid press. How do we do that? We start by making an assumption, which is, let's assume that when we boot this system up, nobody's pushing a button. Okay? Because you're turning the system on. So in reset, right, the first time you scan the keypad, and it's come to my attention that I'm going to change the way that I represent this, because scan there makes it suggests the existence of a function. And so some students have interpreted this as they should write a scan function. Scan there, every time that this keypad thread gets scanned, the first part of this thread is the scan, right? So the scan is occurring at the top of the thread, right? So we turn this on. The first time the keypad thread runs, we scan the keypad. That variable I assumes a value. Either it's a key -1 for no key or some number for a key. The state that we are in will be not pressed. We're assuming that no button is pressed on the keypad. We ask ourselves, is the key code that we just read -1, which is to say we did not read a valid key press? In the event that we read a key code of -1, no valid key press, we just stay in the not pressed state. And that thread will then yield, and it'll get scheduled again, and we'll take a different action, right? So in the event that we read no key press, we just stay in the not pressed state. In the event that we do read a valid key code, right, the variable I has assumed some number between 0 and 11, then we transition to a maybe pressed state. We aren't yet convinced that the keypad isn't bouncing, right? But we've read a valid key press. We store the value of the key that we just read in some variable that maybe you call possible, right? That is to say, let's say we read a key code of 5 right here, right? Let's say the variable I assume the value of 5. We would say, okay, possible is equal to 5. It's possible that I'm pushing a 5. We'll see. But we're going to scan the keypad again and transition to the maybe pressed state. In the event that the key code that we read this subsequent scan of the keypad matches the one that we read last time, right? The key code is the same as possible. We read 5 again, for instance. Then we have confidence. I'm sorry. If we don't, then we transition back to -pressed, right? In the event that there is a match, we transition to the pressed state. We are confident that the keypad is not bouncing. We've read the same key 2 subsequent times, and so we're going to assume stability here, and we transition to pressed. In the event that there is not a match, we go back to the not pressed state, and this cycle repeats until we get 2 subsequent matches. So now we're in the pressed state, and for as long as we continue to read the same key code, we stay in the pressed state. We're still pushing 5, or whatever the value may be. As soon as we measure a -1, the user might have lifted their finger, and so in a directly sort of analogous very analogously to the way that we transition to the maybe pressed state here, we're going to transition to a maybe not pressed state here and do essentially the reverse exercise, right? We're going to scan the keypad again. In the event that we read a -1 again, we'll transition back to the not pressed state. In the event that we read the key code again, it bounced shut again, we transition back to the pressed state. So it takes 2 subsequent reads of a valid key press to go from not pressed to pressed. It takes 2 subsequent reads of an invalid key press, a -1, to transition from pressed to not pressed. Yes? The scans are every 30 milliseconds. This raises an interesting question that a number of students have pointed out, which is, there appears to be an implicit assumption here, right? Which is that describes something about, we're making some sort of an assumption regarding the rate at which we're scanning the keypad as compared to the rate at which it is bouncing, right? So you could imagine if we had some system that bounced really slowly, that this, if we were only scanning the keypad every 30 milliseconds, this would not be a very good mechanism for debouncing it, because it would bounce open, we'd measure 2 subsequent opens and go, oh, it's pressed, and then it would bounce shut, right? So it does suggest it suggests that we are scanning the keypad at something like the rate at which it is bouncing. And indeed, if we scan this every 30 milliseconds for this particular set of buttons, we are. But it's an absolutely correct observation that the first step of implementing something like this is characterizing the button, scoping it, pushing the button, and seeing what's my bounce rate, so that you're timing a software solution to this debouncing problem, so that you are debouncing at a rate that is appropriate for the rate at which the button's bouncing. In this case, I can assure you that we are. You could check this yourself on the scope. Okay. There's one more piece of clarity to add here, which is the lab 1 specification is that you get 1 sound per button press. So let's say you have the chirp on button 2, so that when the user pushes the button 2, a chirp comes out. The user should be able to push button 2 and hear 1 chirp, and if they push and hold button 2, it's still just 1 chirp. They have to get a second chirp, they have to lift their finger and push it again. The easiest way to implement that is you only take the action that causes the sound to occur, the chirp to occur, when you transition from the maybe pressed state to the pressed state. You don't take an action every time you measure yourself to be in the pressed state. Otherwise, you go chirp, 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 chirp. It's a place to start, perhaps. But if you only take the action when you transition from maybe pressed to pressed, then there will be precisely 1 sound per press. And the user will have to actually lift and press again to get another sound to come out. Yes? Yeah. So you're making the correct observation that last time I stated that if you care a lot about timing, you don't want to use the threads to enforce this timing, because you don't know exactly when that thread's going to be returned to. So in the event that your application included another thread that was going to be hogging a lot of CPU, then yes, some other mechanism you'd have to come up with in order to get, on the order of tens of milliseconds scanning of the keypad. In our case for lab 1, you will probably only you'll have your interrupt service routine that's actually doing the audio synthesis, and then you'll have the keypad thread, and perhaps you'll have one other thread that is sort of scheduling each sound, but probably not more than that. So in this case, though we can't guarantee that this thread will be run exactly every 30 milliseconds, it's close enough for this human rate stuff that it works out okay. It's a good question. Other questions about this? The next thing I'm going to talk about, just incidentally, is what's that action? So let me just mention, in lab 1, this week in lab 1, you're going to be integrating 2 demos, like I said. The demo that just produces beeps over and over and over again, and then this other demo that's just scanning the keypad and printing out the button that's pressed. What I would recommend in this, so first of all, it raises a question. Which is the easier direction of integration? Is it easier to bring beep beep into the keypad code, or is it easier to bring the keypad code into the beep beep example? I recommend bring the beep beep code into the keypad example. So open up the keypad code, get it, just load it up and get it running, and then separately open up the beep beep code and bring it into keypad. And as a first exercise, what I would recommend is get those two actions occurring purely independently. And so you'll bring these two together. The beep beep part of the program will be producing these beeps over and over and over again. And simultaneously, you'll have this keypad thread that's printing out the value of the button that's being pushed. But the two processes don't know about each other, right? The next step then is to make them aware of one another. And what I would recommend as a next step is change the interrupt service routine for the beep beep code very gently, and I'll show you how in just a moment, such that it doesn't automatically produce a new beep. And then move the logic that currently lives in the interrupt service routine that transitions it back to produce another beep, move that logic down to the keypad thread so that when you push a key, a beep comes out. So you go beep, 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 beep. That's a great first step. And then as a subsequent step, you can change the beep to, say, a swoop or a chirp or something like that. And then you can augment the interrupt service routine a little bit so that this button means swoop, this button means chirp, and so on. So I'd recommend bringing them together, first of all, totally independently, and then tie beep production to a button press, any old button, or all the buttons, any of the buttons, whatever, and then change the sound from the beep to a swoop or a chirp. But I'd like to talk a little bit about this action here, right? That first step in integration, which is producing a beep from a button press. And let me start this conversation by pulling up the audio production code that we've been looking at so much here, right? This is the beep beep code. I mentioned previously that all that the interrupt service routine in this demo is doing is producing that beep using direct digital synthesis. There's a few extra lines of code here to implement a few things. You'll notice that this has a very simple state machine. This state machine is in one of two states. In the event that it's in state 0, it is producing sound. In the event that it is in state 1, or the other state here, it's not producing sound. And in fact, all that it's doing is incrementing this variable. It's counting time in units of interrupts until it gets to some threshold, at which point it zeroes the output amplitude, transitions our state back to state 0, and zeroes this variable that we're using to measure time. This automatically transitions us back to beep production. And state 0 up here, incidentally, this is doing a bunch of stuff that looks very familiar, right? We spend a bunch of time talking about direct digital synthesis. There's our two direct digital synthesis lines right at the top. Increment our phase accumulator and do a little bit of fixed point arithmetic there. Again, forgive me, I'm gonna talk about that in detail on Wednesday, but all that we're doing is multiplying our amplitude, a value between 0 and 1, that allows for us to ramp on sound, by the output of our sine table. We are, in the event that we're ramping on the sound, we make our amplitude a little bit bigger or a little bit smaller in the case that we're ramping it off. We mask our data bits into this DAC data 0 unsigned short, and we do an SPI transaction. We increment our counter to see how long have I been producing a beep, and in the event that we have gotten to the beep duration, we transition to the other state. So the only things that are different here as compared to the previous DDS code that we were looking at is we're taking the output of our sine table. In the previous example, that was always a full amplitude sine wave. All that we're doing here is multiplying the output of the sine table by a number between 0 and 1 that allows for this to modulate the sound on and modulate the sound off. Remember that if we don't do that, the effect will be you'll hear a click at the beginning of the beep and a click at the end of the beep. There are two ways of thinking about that. One is if you go from no amplitude to full amplitude or the other direction, you're hearing all the Taylor series sine waves that compose that sharp transition. You hear them all at once, sounds like a click. A more physical mental model for this is the voltage that we're sending the DAC specifies the position of a physical membrane in the speaker. If that membrane's at rest and then you suddenly go full amplitude, it's going to go boing, 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 like this, right? Because it's a physical system. That boinging contains all those high frequency sine waves that I was talking about, and it sounds like a click. And so you want to gently move the membrane and then gently stop moving the membrane. So we ramp it on and we ramp it off. It's also, by the way, physical. This is what birds do, right? Because they're producing their sound via anatomy, so they can't impulsively turn a chirp on. Okay, so all that this interrupt service routine is doing is getting a sine wave amplitude, modulating it on or modulating it off, and sending it to the DAC. After it has measured that it has produced a beep for a specified amount of time, it transitions to this other state where it is not producing any sound. All that it's doing is counting off a certain amount of time, beep, repeat interval, number of interrupts, at which point it transitions back. And in order to transition back, it zeroes its modulating amplitude. It says I'm going to start ramping it up again. It transitions our state back to 0, and it zeroes this counter so that we start counting up time from 0 again as well. So this action, right? In order to produce a beep every time you push a key, the easiest, most sort of surgical way to do this with the least disruption to the code is to say, okay, all I'm going to do is modify this interrupt service routine by essentially, hold on a moment, screen, share. I see. Okay, let me bring this here. Okay, that's the wrong one. Hold on. All that we do is modify this interrupt service routine very gently so that we say when we get to this else statement, we comment all this out. Once we transition to the other state, the interrupt service routine will never automatically transition itself back. And then what we do instead is we go down to, we will have integrated this keypad scanner. Like I said, underneath the keypad scan, you will have that statement, the debouncing state machine that I just described. In the part of that state machine where you transition from your maybe pressed state to your pressed state, you include these 3 lines of code. So that every time you transition from maybe pressed to pressed, you zero the current amplitude, you set the interrupt service routine state back to its sound producing state, and you zero the counter so that the interrupt service routine starts counting up again. If you do that, then this will produce a beep, never produces a beep again. When you push a button and transition from maybe pressed to pressed, another beep will come out. By the way, if you push in less than whatever this beep duration is, I can't remember how long it is, but if you re-push in an amount of time that is less than the beep, it'll go beep, beep. So it'll start the new beep before it has finished the previous one. That's okay. You can change that if you want to. This is, I've gotten a question from a few students, which is, if we're producing a chirp, say, and the user lifts their finger and pushes the button again before the chirp is done, what should we do? Should we wait for the previous chirp to end and then make the new one? Or should we interrupt the ongoing sound? You can do either. So, some people prefer the former. Some people prefer the latter because it feels a little bit more responsive. Neither is really any simpler than the other one, so whichever gives you the experience that you're after is fine with me. Any questions about this? Let me remind you too, just one more quick little reminder. If you go to the Lab 1 webpage, sharing the right screen here. If we go to the Lab 1 webpage, there is reading here that describes Birdsong synthesis via DDS. This gives you the mathematical infrastructure for mapping these frequency sweeps to functions. This web page maps that little swoop at the beginning to a sine wave, the chirp to a parabola. Let me just remind you that this web page assumes an audio synthesis rate of 40 kilohertz. In Lab 1, you're using 50 kilohertz. You just have to adjust this a little bit. But everything else should be the same. The only thing that changes here is the synthesis rate. And so if you use this as a model, it should be as simple as plugging in a few different numbers, but I want to give folks the opportunity to do that. Yes?
So for the settings to swoop sound, do you also use a parabolic function?
You could. So it's a good question. This web page maps that swoop to the top of a sine wave, the first period of a sine wave. You could absolutely map it to a parabola if you cared to. That might look like an exponential to you. The thing to consider is how expensive is one mathematical operation as compared to another mathematical operation. You're trying to do this interrupt as quickly as you can. We're going to talk through some sneaky tricks with regard to these particular functions here in a subsequent lecture. Yeah?
So, I mean, if you pre-compute the values, would it still really matter?
That would absolutely be the fastest way to do it, but I want you to make a synth. So you're making the observation that if you pre-compute these values and store it in memory and just play back, that's certainly the fastest way to get in and out of that interrupt. I would like for you to generate these sounds in real time. Make it a synth. In another semester, I'm going to switch birds so that the sound is long enough that it doesn't fit in memory. This was an oversight on my part. That was true for this bird on the PIC32, the previous microcontroller that we used. No students could get away with that. Turns out they can with the more memory, and I didn't realize that. By the way, I said that we want to compute this stuff as fast as possible. One way to produce this sine is with the math.h function, right? There's a inbuilt C library to produce sine. But didn't we just spend like 2 lectures talking about how to produce sine waves really efficiently? Right? So one might consider making one more DDS synthesizer here and synthesize that sine wave. Right? That's so much more efficient. Let me just say too, this parabola, right? In order to compute a parabola, scroll down a little bit. That requires at least one multiply and an add, which isn't so expensive, but that multiply is a little bit expensive. Yeah?
When trying to do this, at least with the sample frequency theory thing, so I think it worked fine for 2 kilohertz to 7 kilohertz, but when you shrink that, so it sounded kind of like part where we had to pre-compute everything because of resolution issues. Like we couldn't get the increment small.
Okay. We'll talk about that. You should be able to.
Okay.
We'll talk about but I want to just point to this function. Some of you may have in the past used the inbuilt C function pow to take a number to the power of some value. That is so slow. Like if you use the scope to measure just how long it takes to compute pow, it takes forever. It is so much faster than that to say, I'm just going to take x and multiply it by x. The multiply is faster than the pow. Even faster than that, you could remember the fundamental theorem of calculus? The value of a function is equal to the integral of its derivative, right? So you could make the observation that the value of this second order function is equal to the integral of its derivative. The derivative of a parabola is a linear function. And you don't need a fancy integrator here. You could do a straightforward Euler integrator. The consequence of that would be, instead of computing this function to get your frequency at each time step, what you would do instead is Euler integrate the derivative of that function, and it changes all this math into, I think, a shift and an add. Even faster than the multiply. These are the kinds of fun games, right, to play. So we know what we want, and now the exercise is to figure out how could I get this as quickly as I possibly can. I will ask you not to pre-compute it. I'm going to make this memory prohibitive in subsequent semesters. Don't do it this semester. You have to compute this in real time. How do you do it as quickly as you can? multiplies faster than PAL by a lot. Integrating the derivative is even faster than that. I can't take credit for that idea, by the way. That was Bruce's idea. Okay, I will be in lab this afternoon. Hopefully this recording didn't get all screwed up. We'll see.